Hello, in this video we're going to look at solving a system of equations with matrices. So in this problem we have a system of three equations. And usually we solve this by process of elimination. We eliminate the x there, and then the y there. And typically after those three steps, we're able to solve and find our answer. However, this time we're going to use matrices, and really the process is almost exactly the same, just the format or the look of it is different. So we are going to take this and convert it into a 3 by 4 matrix. So we understand the basics of matrices. It's an array of numbers, a collection of numbers. And when I write this matrix, all I do is I take the coefficients of each equation and write them as the entries in the matrix. I just drop all the variables. So for the first equation, I go 1, -2, 3. For the second one, I go -1, 3, 1. And the next one, 2, -5, 5. I just dropped all the variables. But I didn't write the whole equation. I have to include the answers to it, what is on the other side of the equal sign. This is where we call an augmented matrix. A lot of times you have those 3 dots separating the system part of it from the answer part. So here I'm going to put 9, -2, 17. The 3 dots are sort of to symbolize that there's this break in between it. These ones are dealing with the system. These ones are dealing with the answer. So the 3 dots kind of symbolize that break in it. But we want it all together in one matrix because we're going to do operations with the whole row, all 4 columns at once. Now, our idea when solving this as a matrix is exactly the same as before when we had the variables. We're going to try and eliminate that, and then that, and then that. And hopefully we'll have the answer we need after doing that. Okay, let me get back those numbers. Now I want to slide over here and kind of show you what our final answer is going to look like, along with talking about some special words. First of all, row echelon form. So row echelon form is when every leading number is a 1. Basically on each row you have a leading 1. The leading number is the first number in the row after zeros. So the 0 is not the leading number. We go to the first number with an actual value. And when those are all 1, we call it row echelon form. That is compared with something called reduced row echelon form. That's where at every leading 1, there are zeros below and above it. So for this one, you got a 0 above and below. And for this one, there are zeros only above it. Notice how in our example above, it's not reduced row echelon form because I have zeros there, a 0 here, but when I go up here, I have a 2. So it's not quite reduced row echelon. Basically, when solving these systems, you get it to row echelon form, and you can stop and actually find the answer from there. Or you can keep doing elimination, and you go back up the problem and eliminate those, and then eliminate this to get it in reduced row echelon form. And you might see the advantage to that, because when it's like this, I immediately know the value of this variable. It's 3. The value of this variable is 2. The value of this variable is -1. Whereas with row echelon form, sure, I know this one, turns out I know this one, but in order to find this variable, I'm going to have to solve a little equation with substitution. Okay, but there I just wanted to define a couple terms, row echelon form and reduced row echelon form. Again, row echelon form is when you have all rows with a leading 1, and there are always zeros below the 1, like that. Okay, let's go back to our system then. So how do we actually solve this? The same way as a normal system. We're going to add rows together, maybe multiply and then add in order to eliminate variables. So for this first one, I'm going to go row 1 plus row 2. And I'm going to do this directly in the matrix. Because sort of using a matrix is all about making things more efficient. So my first row is going to stay the same. So I can write it as so. But then I have a new row 2. So here we go, let's talk verbally. 1 plus -1 is 0. -2 plus 3 is 1. 3 plus 1 is 4. 9 plus -2 is 7. And then I'm going to have my same third row. Now, in order to eliminate this 2 here, I'm going to have to add with the first row. So what am I going to do? I'm going to do -2 times row 1 plus row 3. So first, and you can do this with less steps, but I'm going to multiply that row 1 by -2. So here we go. And in fact, you know what? Because this is kind of an intermediate matrix, I'm going to change the color. So I go by -2. So -2, 4, -6, -18. Hopefully I make no mistakes because there's plenty of room for errors when doing this. Lots of quick calculations. Okay, there's that intermediate matrix. And then we'll move on up over here in the new third row. Well, if I go -2 plus 2, that gives me 0. 4 plus -5 is -1. -6 plus 5 is -1 as well. And -18 plus 17 is also -1. Okay, the same second row. And now for the first row, I'm going to go back to what I originally had right here. Okay, before I multiplied by 2. So 1, -2, 3, 9. Next thing I need to do is eliminate this right here and make that a 0. So to do that, I'm going to go row 2 plus row 3. No multiplying required in this one. So same first row. Same second row. And then I add these together. 0 plus 0 is 0. 1 plus -1 is 0. 4 plus -1 is 3. And 7 plus -1 is 6. Now this is enough to solve the system because you can imagine having your variables back here. And notice how I could find the value of z right now. It's 2. But it's not technically in row echelon form. So I'm going to get it into row echelon form. How do I do that? Well, I need leading 1s in every row. So I need to divide this last row by 3. So I go 1/3. I'm going to go 1/3 times row 3. That's what I do in this step. And that gives me 1 and then 2. You can either keep with your matrix and solve it. You can slide in your variables here if you like that method. Or you can just rewrite the system with all the variables. And that's how I'm going to finish it out, just to make it real explicit. So I have 1x minus 2y plus 3z equals 9. And then I have y plus 4z equals 7. And the easy z equals 2. All right, so now to solve this, I know that z is equal to 2. And then I can go y plus 4 times 2 equals 7, giving me y plus 8 is equal to 7, so y is equal to -1. And lastly, to go back up to the top and substitute in both known variables, but z is equal to 2. So I have x plus 2 plus 6 equals 9, x plus 8 equals 9, so x equals 1. I have my answer, and I can write it as a nice ordered triple to finish this off. 1, -1, 2. And that's the answer. And that's how you solve a system with matrices. Basically the same as solving a normal system, except you take away the variables. And it can be nice and slicker, cleaner looking, which is one of its advantages.